So, good afternoon, everyone. I feel like I'm giving a docent talk. Thank you to docents especially for coming out today, but thanks to everyone who's here. I know you'll be richly rewarded by today's talk. It's a great pleasure to introduce, I'm Louise Court, Curator for Ceramics at the Freer and Sackler, and the Curator of Cranes and Clouds, the Korean art of ceramic inlay, which is the exhibition that just opened last weekend that provides an occasion for us to invite back to Washington Dr. Pamela Vandiver. Pam was at the Smithsonian as a senior research scientist for 18 years, working in topics of ceramics and glass at the Smithsonian Center for Materials Research and Education before she left in 2004 to move to the faculty of the University of Arizona. And she is working there now. I've learned of Pam that everything she does has multiple dimensions. And at the University of Arizona, she is professor of materials science and engineering with a joint appointment in anthropology and archaeology. And she is co-director of the program in heritage conservation science in the Department of Materials Science and Engineering. And no doubt she's doing several other things that I don't know about yet. She is a leading scholar in the technological characterization of ancient materials, the reconstruction of their technologies of production and use, and the interpretation of their cultural and/or artistic significance. Her work has concentrated on Paleolithic pigments and figurative ceramics in Europe and Asia, on Neolithic plasters and the beginning of ceramic pottery in East and Southwest Asia, as well as on the physical chemistry of Chinese glazes, tin smelting slags from Göltepe in Turkey, Egyptian faience, and the development of European porcelain, among many other topics. Recently, she has been working to reconstruct the ceramic technologies from Angkor in Cambodia and to see them relearned and to see the craft knowledge preserved as intangible cultural heritage. Another recently completed project involves analysis of Glaze tile technologies based on ashing of desert plants for reconstruction of monuments in Samarkand and Bukhara in Uzbekistan. Pam Vandiver has 2 master's degrees, one in art and anthropology and the other in materials science. She spent 13 years in the Department of Materials Science and Engineering at Massachusetts Institute of Technology, where David Kingery was her thesis advisor. And Kingery and Vandiver put together the wonderful book, Ceramic Masterpieces, which, if you don't know it, all of you should have on your bookshelves. So it's a wonderful pleasure to introduce Pamela Vandiver, who will be presenting a talk called Cranes and Clouds, the Evolution of the Inlay Technique in Korean Ceramics. And this talk is made possible by the generous support of the National Museum of Korea. Pam.
Thank you for that kind introduction. When I did the study of Korean ceramics, it was mainly in the 80s and early 90s. So many of the words that are Korean that have been transliterated are going to be in the old system with the hard P instead of the soft B. So just please bear with me. Many times I've used both of them. Instead of Goryeo, I've used the harder Koryo. So I'm sorry that I haven't updated everything. I welcome your questions. I think after the lecture it would be very nice to spend some time in the gallery looking at individual pieces and discussing them. As well, since this is such a small group, if you have questions, please don't hesitate to interrupt. I'm going to first show some pictures of from the, unfortunately not really good ones, but ones that I took yesterday afternoon on the fly, but ones from the exhibit where I spent most of yesterday afternoon. And actually I met a couple of you in the exhibit yesterday. So I look forward to seeing you again. So an inlaid bowl with both black and white, decoration of flowers and phoenixes, an example of reverse inlay, where the black inlay is applied to the background. So I'm going to go back a slide, I hope. This technique is the carving very precisely of inlaid decoration that resembles that done in metals and in lacquer and probably in textiles. And over time, it develops and changes. And this type of style has been very well studied. This we have no sherds from. Ihwa Women's University in Seoul has done a wide variety of kiln excavations, but they found, at least as of about 5 years ago, no shards that resemble this kind of reverse technique. So we really don't have much any archaeological information about this technique. So because we don't have sherds, and we really shouldn't be using an original and taking samples of it, and we really don't have the non-destructive means to look at both composition and microstructure, it really has not been studied. So this is the later inlay practice where the inlays are stamped and drawn and sometimes incised, where the inlay is applied over a larger area. These come from mostly the 14th century. And then these are much later, 15th century, Bunjeong from Joseon dynasty. And here we have stamps that oftentimes have multiple parts. So here you can not see, but you can imagine that the stamps are actually made of several different circular pieces of bamboo or other material that was impressed in the ceramic, and the white slip was then coated over the entire surface and then scraped or removed. So the visual effect is very different. The ceramics that we see here are primarily quartz ceramics, and in Koryo Dynasty and in Choson, they're replaced by porcelain. So a technology that had a very refined development, a very high standard for court and nobility, became a common people's technique, perhaps for those who had some status, but became a more common wear. And Louise in the exhibit has noted that many of these pieces have a very soft, almost whitish appearance. And we think the inlays here contain much more clay and much less quartz. So they're much more fluid when they're applied, and the technology actually changes over time so that there's less control on the application of the inlay. So I'm going to show some compositional and structural features of the black and the white inlay. There are also examples where the clay is just painted, the white clay is just painted directly on the bowl and not sanded away or scraped away or carved away, but becomes what I think in Japan would be called hakime. That would be a brushstroke impression of the movement of the brush, which is really very exciting. In addition, there's a wonderful sherd that does not have any glaze on it, but that just has the white and the black inlay in place in a bisqued or low-fired shard that would then be glazed. Now, oftentimes when one talks about science, one thinks that one can come up with an experiment that's completely devoid of context. And in the more descriptive sciences, geology, for instance, the study of museum artifacts, biology, one doesn't just design an experiment independent of context. Instead, one uses every possible scrap of information that one can use and then develops the research problem as one looks at preliminary data. So in a museum, and the Freer is one of the prime examples, there's a research team, a collaboration between people with expertise in different areas, and we meet and we talk and we discuss how similar a sherd might be to a whole piece, and if we took a sample of the sherd, what it would actually say about the piece that is preserved in the museum collection. So we oftentimes will visit together archaeological sites or go to conferences in order that everyone will share the same kind of depth of knowledge of that particular artifact, that particular genre of artifact. When we use science to reconstruct technology and to learn about the practice of art, there are 5 different models that we apply to that study. We can differentiate the weathering and corrosion on the surface of an object from an original craft technology and its raw materials. We can reconstruct the relationships between materials, their structure and composition, the properties, for instance, the visual appearance, the processing, how something was made, and the performance or the function. So in the Second World War, the field of material science came into being with the development of the atom bomb. And it was an interdisciplinary project that put together physicists, chemists, engineers, mathematicians, and people involved in the evaluation of materials. So chemists primarily at the time, but some geologists. So this idea of studying materials in this way developed, and it became the basis of ways of funding science at the National Science Foundation after it was established after World War II. So a modern material scientist or solid-state chemist would try to have a particular performance, superconductivity, for instance, or a photovoltaic, an efficient photovoltaic panel. And then they would work back through various materials that might do this. They'll test a whole variety of different materials, look at structure and composition. They'll measure properties. They'll try and develop some kind of innovative and inventive processing. And this really isn't very different from what craftsmen in more ancient times actually did. They studied their local raw materials, and they practiced doing different things. They looked at different properties and evaluated them, and then tried to figure out what in the processing was peculiar to a particular visual effect. And then they would also interact with customers or with people who knew a lot about the particular visual effects that were desirable in ceramics. So again, this is a very collaborative kind of thing. We can observe and analyze materials at different levels of scale with different analytical techniques to yield desired information. And we usually start with the biggest object, the largest chunk of material that we possibly can, and then work down to the scale of atoms and light waves. Oftentimes, the sequence of production steps and their variability can be related to visual appearance and performance characteristics through analysis and replication. So very oftentimes, we will try to work with a craftsman or with materials derived from a particular area and try to replicate. With modern material science, we start with the purest possible material, and then we process it. But if I deal with an ancient material, it is going to be a horror story because it is a mixture of materials. So many of the techniques developed by modern material science are inapplicable to ancient materials, and we also don't have large samples of many ancient objects. So the idea that we can take a very small sample, cycle it through many different techniques, but also come up with similar raw materials and then carry out our own replication. And sometimes that replication, because we know what we've done and what we selected and we've characterized it before it was fired and after it was fired, we can actually have a standard, a working standard that we can use for comparison. And then finally, the reconstruction of firing pyrotechnology is very important to understanding the optical appearance of many ceramics. So this is what my students call the line model. So we proceed from artifacts through a variety of degradation processes to culturally significant objects and work our way back to raw materials through a variety of operations or through technology. This is the standard material science paradigm, which means that we can, as a studier of ancient materials, we can measure exactly materials, their structure and composition, their properties, appearance, strength, durability, etc. But we have to reconstruct, conjure, imagine, anticipate, replicate the processing as well as the performance. We also use a couple of different how would you say, philosophical models. The chain operatoire is a French archaeology model. It means there's a chain of operations that defines the end product from the raw materials. And it involves behavioral aspects, such as training, such as reuse, such as exchange and gifting. And when we come up with this, essentially what an engineer would call a systems engineering approach, we really try to identify the links that define production. What are the steps that limit production? Essentially, we want an analysis of flaws, errors, industrial debris. We want to find out what the rate-limiting steps or the steps or operations with which craftsmen or artisans were having problems. What's the range of variability or the range of standardization? And these are really the critical questions when we start to look at processing. And then here we are doing analysis at the level of an archaeological field excavation and working our way down to electronic structure. And right here, this boundary between what we can see, which is generally larger than 100 microns for most of you who are 20 years or younger, but it's much coarser for me, who is approaching 65. These are the features that we can actually see, and we can conduct a forensic examination to find out, how it was used with its scratches and chips and potential residues in cracks. And then we have to go to equipment, microscopic equipment, to see much finer scale, but lots of the interaction that makes up a ceramic or a glass or a metal really occurs at this finer scale. And then this is from an old Scientific American article I wrote on glazes. Different kinds of glazes require different kinds of heat treatment. So the feldspathic or the Chinese lime glazes are here. Oftentimes they're wood or coal fired, and so the temperature goes up and down, and that will cause nucleation and growth of different kinds of crystals. So this idea of adding fuel to the fire and keeping it at temperature for some time actually leads to different visual appearances, whether something is clear or it's got lots of crystals in it or it's got a few crystals in it. So I'd like to show you a couple of examples of that. We've recently been analyzing some roux-ware from the Chiang Liang-Se kiln with a scanning electron microscope. So I want to show you a couple of examples. So this is the glaze. These are the bubbles. We can tell which way it broke because on the far side of the bubbles there oftentimes is a little step fracture. So this fracture went in this direction, the fracture went around the bubble and then collected at this far side. We can also see if I drop a Coke bottle on the floor, if there is such a thing anymore, I'll see conchoidal fracture. It looks like a clamshell. In other words, the fracture radiated out from the point of initiation. And here there are no clamshell-like fractures, and instead we see we've got some rough surfaces, some smoother surfaces, and the fracture goes up and down through this in a very convoluted way. So we know we've got crystals and chunks and heterogeneities, and this is a mixture of glass and crystals that makes the jade-like appearance of roux-ware. So this is the Glaze body interface, and that's what the body looks like. It's got chunks of quartz and all sorts of things in it. So this is a polished surface that has been hydrofluoric acid etched. These are quartz particles. This is glass. This is a darker color right here. And then these are mullite needles. So many of you, are aware how wonderful China is and what porcelain is. And when I taught in China at Northwest University of Science and Technology, one of my students asked me, "Where is glass?" And I had to tell him that it occurred that there was no such place, and he said, "But that's really the most wonderful invention of the West." And I had to say it's occurred at the meeting of three continents that have had an amazing political history with a lot of the problems through time. So he said, but it's so wonderful to be able to see through it. We really can't do that with the Chinese ceramics. And I said, but look, what you've got is a composite body. And so as you heat up the kaolin, and sometimes there's another kind of clay called illite, and sometimes there's a little bit of mica in it, particularly with the southern bodies. So as you heat it up, the low-fired materials, calcium, potassium, will start to melt and form this glass. And then as this glass comes up to temperature, the alumina and silica will separate out, and it will form these wonderful needle-like, lath-like particles that will hold all of these quartz particles in place. And the quartz particles slowly will start to dissolve into the glass, and some of the silica will actually come and help to form these mullite particles. And then what will happen is the quartz reaction layer, as the piece cools, will form what the Chinese microscopists call a horse's tooth pattern that is a cristobalite. So what we have here is something that as we heat it up, instead of melting and flowing and depositing a large glassy lump at the bottom of a kiln, actually becomes more stable, becomes stronger. It may flow, it may warp, and that's very, very common, and all Chinese potters had to fight against that when they heated it up to a high temperature. But essentially we have something that becomes more viscous as you heat it up, because more of this mullite is crystallizing out and more of the silica is going into the glass and increasing the melting temperature of the glass. So it's this absolutely incredible material that nobody who's used to heating something up and melting it could even possibly imagine. All right, so this is the glaze, and this is an etched surface of the roux-ware. So there are crystals that grow in the glaze, and these are a calcium aluminum silicate crystal. And what's really wonderful about them is that they're layered. So you can see they've got kind of a right angle here. That's because feldspars have a crystal structure that's got right angles in it, as opposed to quartz, which has got hexagonal structure like a honeycomb. All right, so what's happened is calcium, alumina, and silica have formed this crystal, but the crystal hasn't formed homogeneously, it's zoned. In other words, there's a layer that is mainly calcium and alumina, and then there's a layer that's etched out that's primarily silica, and then there's another layer of the calcium aluminum silicate, and then there's a layer that's enriched in silica. So the silica is actually a higher melting temperature, but it etches out with the hydrofluoric acid. So we've got these needles. If you look at the microstructure of jade, which I keep meaning to do, you'll also see lath-like crystals. What also has happened is when some of these constituents have been taken out, the resultant residual glass in the glaze is more stable as two liquids than one. So it's formed something called liquid-liquid immiscibility that most of you know every time you use oil and vinegar salad dressing on your salad. They're two individual liquids that are more stable than the mixture of the two, but if you shake them up, the liquid becomes translucent, not transparent. And it looks like this. They're small globules of one thing in another. And that's the same thing that's happened here. So I'll show you a close-up. Instead of 10,000, we're now up at 70,000x. This is one of these crystals. And what's wonderful is that we can really get behavior from this. You're going to think this is really obtuse. I'm here to hear about Korean ceramics and not Ruware. Well, what's happened here, this zoning, is that the potter put in, as the kiln was coming up to temperature actually, the calcium aluminum silica began to crystallize out. And then somebody threw in a load of wood, and this composition right here started to crystallize out. And then that wood burned down, and this other phase of this anorthite crystal continued to grow, but it was richer in silica and then richer in calcium alumina. So this is actually 3 loads of wood that were added into the kiln during the formation of this crystal at high temperature. So we actually have some behavior of the potters from the microstructure. So I wanted to share that with you because I think it's just really fantastic. And then this is the liquid-liquid phase separation. All right, so here we are. Pottery production sites, a lousy, and many of these are going to be yellowed. I am not a good photographer. So what we see is that the collision of 2 continents about right here, like about this. So the materials here, here, and here are very rich in mica and illite and not so rich in kaolin. The materials here, let's see, here, and some of them, they're mixed with volcanism in Japan. So here you've got the most complex panoply of materials you could imagine. Louise and I one time stood in the Minoseto area at the bottom of a quarry that was about 100 feet deep, and you could get every material for glass and ceramics that you could imagine in gray and white and yellow and brown, and just absolutely incredible. But many of the materials that are in Mongolia and in this whole area are very poorly weathered. They require a lot of grinding. They are they've got more alumina in them. They're 2-layer, much higher temperature, kaolinite, and they go from coarser, less weathered at Yaozhou that requires 1,300 degree temperatures. And it's one of the craziest ceramic traditions you can imagine because everything is always overfired. And then or extremely high fired, and then to the lesser firing temperature materials here in the north of Korea, and then in some of Japan. All right, so here is chronology. So we have unified Shilla, and before unified Shilla, high firing kilns come into China in the 3rd through 5th century, as do intentionally formulated glazes and this special Chinese technology for the production of gray stoneware. This technology really doesn't go into Japan until the 800s. These gray ceramics are impermeable, although they're called stoneware, and they're very, very strong, 2 to 3 times as strong as typical red ceramics. But that's a story for another day. All right, so before we start our science, we have a collaborative interaction and try to get the history right, the archaeology right, and the ceramic research correct. So Chinese Yue glazes from Zhejiang were admired and placed as offerings in high-ranking Korean tombs of the unified Shilla. Let's see, so here we've got inscribed Proto-Celadon in 993, and then 1157 inlaid Celadon found in a tomb. All right, and then Yue Celadons were studied and imitated in Korea, for instance at the Sori kilns, where a great amount of experimentation occurred, as exemplified by the variation of white to green glaze colors, compositions, and firing regimes. So at Sori, there are 4 kilns, 2 imposed over 2 others, or continuations of the same kilns, and you go from very, very white to very, very green to very, very blue. And if you sat there and tried to throw things into piles of Celadon and white, you would not be able to do it. You'd have a rainbow, just a continuous panoply. So I've got analyses of probably 60 of these ceramics, and very rarely are 2 the same, are 2 really similar. And a study's been carried out by Carolyn Cho in Korea of the examples that were very clearly representative of green or of white. So our results are very different. Let's see. During Koryo dynasty, celadon produced in Kanjin and at other sites was adopted as an imperial ceramic, so important for establishing and maintaining cultural identity. An innovative Korean contribution to world ceramics was the use of black and white inlays placed beneath the glaze to depict images such as clouds, cranes, and flowers, often accompanied by a crackle pattern, and I'll go into the crackle pattern. Observation yields an optical effect of the image floating above the surface of the pot due to increased reflection and local brightening from the internal surfaces of cracks. Poets and others have described flights and floating images during banquets. So I myself have been at some of these banquets, and indeed the place where a crane or a flower is has much more light. It does appear to be floating above the surface, and there are stories of the cranes taking flight. During the Chosun period, porcelain became the preferred quartz ceramic. Celadon became a popular ware and a Buddhist ceremonial ware. The time-consuming carving and inlay techniques of Koryo dynasty celadons, the large quantity of materials used in the thick jade-like glazes, and the necessarily long firings with high fuel consumption and careful control were cut to an efficient and sustainable minimum. So we'll get into glaze thickness later. So stamped and incised decoration was filled with various white slips applied all over the pots or in a special area. Next, the surface was trimmed or shaved to reveal the underlying pattern. Other processes involved application of the inlay materials as slips, painted or wiped directly onto the body, sometimes followed by painting, incising, and carving. So this was how would you say, not a standardized craft. This was something that allowed for a great deal of variation, a great deal of innovation, a great deal of interaction with the surface of the pot. So it's a very different practice, and it is so lively, and that many people have called it impressionistic or expressionistic or abstract. So whatever those art terms may mean to you, in terms of the technology, it involved a huge amount of variety, a tremendous lack of standardization, and evidence that the potter was inventing and trying to do things that he had not been taught as a child, but it was truly an exciting innovation. All right, let's see. These various processes allowed a complex interplay of layers, color, line, and often a subtle undulating relief. This enlivened expressionistic decoration is sometimes compared to the Suzhou tradition, but Suzhou did not have anywhere near this kind of variability. From kiln to kiln at Suzhou, things are much tighter. Things are produced, by the thousands. That, where one sherd can be put in a place of another very, very easily. The Punjang technology, so admired in Japan and America, had centuries of imperial refinement and technological sophistication before it. And that's really important to remember. So this wasn't something that just developed from nowhere. Instead, it was an adaptation. So these are the samples that I studied in, 1988 about. So we're going to use microscopy. We are going to apply our models, and we're going to look at this variation and diversity of these inventive processes. So these are the samples that I studied. I'm not going to go into the details. We had some comparative material, including a modern piece that a lot of Korean potters have said they thought was really interesting. The modern ware is much shinier, and it has much more potassium in it, so it's got much more mica in it. So it means the older pieces, if they had mica in the raw materials, were more carefully washed or were washed, period. Now that much Korean pottery is actually art pottery, people don't, potters want that shinier surface and accept the difference in technology, because they really think that and believe that they're doing something very, very different from the past. All right, so here's some of the sherds. All right, so we have some early sherds that are carved or with glaze, or that have molded design on them. Here we have some inlaid sherds. This one is the base of a Meiping or Maibiang jar, bottle actually. And here we have some inlays. So this would be the opposite of this pomegranate-like structure. So this is the inside, outside, where the numbers are the same. And I'm sorry these aren't better. And then these are later pieces where the inlay is much rougher, the glaze is much less constant in thickness. And then these are the Joseon sherds with a variety of different techniques. So in terms of glaze, this is my original drawing, and this is what the Art Institute of Chicago did when they published this at the end, so I'm giving you a choice. Punjiang glaze thickness is cut in half or even less than that, allowing the efficient use of 50% or less of the glaze raw materials. There are large bubbles that indicate a lack of crystal growth. The large bubbles and lack of crystal growth at the glaze body interface indicate more rapid firing. The choreo, sometimes the bubbles will be 70% of the thickness of the glaze. The choreo period jade-like optical effect is eliminated and replaced by emphasis on a textured but essentially flat, more pictorial surface. Let's see, is there anything else I want to say? The craze lines or crackle or crackalure is common in the early Celadon or Changja. It is present also in the plain Celadon, and then with the inlaid Celadon, the sanggam Changja, it often occurs over the white inlay, but not over the black inlay. So I'll go into that. These are inlay. These are microstructures of the white inlay. And this is in topographic mode. I can change that SEM into another mode, which will bounce things off the near surface and will give me evidence of porosity or atomic number, average atomic number. So in other words, we're just going to call it backscattered. So in other words, if I bounce a basketball off a piece of grass or off a cement slab, I will get a different amount of bounce, a different amounts of essentially reflectivity or backscattered. And so that's what's happening here. So this is bright, it's giving me a lot of signal, so that's a higher atomic number. This is a lesser atomic number, and this is an even lesser atomic number. But if you look at a higher magnification, this has got some porosity in it, so I'm not getting any signal from part of it. This is a chunk of quartz, and I can go in and analyze just this chunk of quartz, and there are a lot of them. So this inlay is made of some glass that holds these chunky quartz particles together, a lot of porosity, and it's put in and it shrinks back a bit. So this is some glaze that's gone into the crack. There are some bubbles and other sorts of things. Let's see, the close-up is at about 30 times more magnification, and it shows these large equiaxed quartz particles that have been sintered together or joined together with a glass that is the glaze. This is the black inlay. This shows a similar, how would you say, a similar average atomic number between the glaze and some of the inlay, but the inlay's got a whole bunch of really weird and wonderful things in it. So this is one of these complex materials, so this is easy to identify. That's a pore, that's a bubble. But these are crystals. These are crystals that are actually these little cubes, and they are magnetite. At the glaze body interface, there are no crystals, so or very few compared to these. So if I look along here, I really don't see any, but if I look here, I see a lot of crystals. So from this evolved microstructure that could have only occurred at a fairly high temperature, what we see is that this black inlay was pre-fired, was pre-made in some way. And then to it may have been added some glaze. We really don't know. So some of the black inlays were probably black from the start, and some of the inlays were red, as you see in the sherd, on display in the gallery. And they would have had a reddish clay added to them. So we think that there's some variability in these inlays. There are lots of areas here that are harder to see, but this is where the concentrated area is that contains these little cubes of magnetite or iron oxide that's black in color. So this is a close-up of this, and this is looking into this area, one of these areas down in here. I figured out where it was yesterday. So these are some quartz particles right here, and these are some of the magnetite chunks that you can't really see, but there are a lot of bubbles. So when it is resintered as an inlay, it remains very heterogeneous and isn't fully liquid. All right, let's see. So this is the glaze body interface right here. These are some residual quartz particles that have started to melt in the glaze. These are the bubbles right here. So a lot of different sized bubbles. This is a partially melted chunk of what is quartz, but it's got lots of pieces of quartz that were originally joined together in some kind of a sandstone. So people refer to this as quartzite. This is the glaze body interface right here. And these are a few little tiny crystals that have just formed. So this is a quartz particle, and these are some crystals that have formed, but very hard to find and generally not present. The presence of so many different, oftentimes irregular bubbles indicates that the glaze was viscous and below its efficient and peak melting temperature. Crystals indicate soaking for a long time or spending a long time at temperature. So, crackle. Low-powered microscope images at about 10x show the translucency of Korean celadon glazes. So this is an early one that was molded. This is one that was incised. And you see some crackle, some craze lines that are oftentimes irregular, indicating that the crack line had to go around bubbles and chunks and whatever in the glaze. If I have a modern Korean porcelain, for instance, and it crazes, I will have cracks that are T cracks that have formed because the glaze shrinks more than the body from being expanded when it was at peak temperature. In the early ceramics and in the inlaid ones that are choreo, these three right here, the crazing continues, but instead of becoming as random, it becomes much more organized and oftentimes follows the pattern of these quartz inlays. The quartz goes through at about 573 degrees C, an alpha to beta quartz transformation, and so what we see is a crack that forms over the surface. The glaze is contracting more than the quartz, but it's happening over a gradual period of time. So the bubbles, the quartz chunks and black particles are barely visible except in the later Choson ceramics. So patterns of crazing indicate differences in contraction during cooling that are sufficient to cause the glaze to crack or fracture. The glaze shrinks more than the body, however, the quartz in the white inlay contracts during cooling and pulls away from the rest of the body, causing the glaze to crack mainly along the edges of the white inlays, a predictable effect. In C, right here, which is a scroll pattern at the base of my byung, the glaze follows the scroll pattern. It connects the dots in the pomegranate pattern, and it spreads out where it ends. So this is the end of the crane's wing. You can see that it's spread out in a variety of directions. So the craze lines radiate but there are no craze lines over the black inlay. Let's see. In Punjong aster impressed decoration, the particles are coarser, and we see, for instance, a rough place in the body. We see black particles here and here. At least you can imagine them if I were a better photographer. The particles are coarser, and the inlay is much thinner. So this is what the composition looks like. It's fairly high in alumina, fairly high in calcium. We can make comparisons between a lot of the Korean glazes. So this is an average of about 21 sherds. And if we look at these, well, for instance, the calcium is in the circles that you can't tell are circles, and the alumina is in the solid dots, but you can't see. But anyway, if this is one component, calcium, which is 19%, and if this is another component, which is alumina, you can see that there's a lot of variation as you go across the glaze. And things like iron that are added and are in solution don't have anywhere near the amount of variability. So some of the interest in a lot of the earlier ceramics are these variations in composition that lead to optical heterogeneities. And in many of the later pieces, right here, there isn't so much variation as there is in the earlier one, but there is still variation. So this is a comparison. Histograms of the glaze composition showing the weight percents of fluxes, in other words, the things that make things melt, and the coloring agents. And I can see it from up here, but I doubt if you can see it back there. But tacked on the end is a little orange chunk on almost all of these Korean glazes, and it's a small amount of manganese dioxide. The manganese dioxide is common in Korean glazes and rare in the Chinese ones. And my belief is that it makes the glaze a little bit grayer. It gives it a richer gray color. The brown areas out here are iron and titanium, and it tends to be lower. These are smaller than they are in many of the Chinese glazes. So here we've got Yue, Guan, Lungchuan, and other northern celadons. And I've analyzed a lot more than this, and that pattern stays pretty constant. These yellow chunks here are potassium plus sodium, and it tends to be lower in the Korean glazes than in a lot of these Chinese glazes. And then the green is the calcium plus magnesium. And it tends to be higher in the Korean glazes, about 10 to 15%, whereas the Chinese ones are mostly 10 to 15. So let's look at this another way. So if I have graph paper that has a triangular piece of paper, I'm going to have 0% of something here at the bottom, and I'm going to have 100% of it up here at the top. So this is silica. So this is 70% silica, so that's the uppermost triangle. And then I can go down to 0% silica at the base. And at the base, each corner is going to be 100% alumina or calcium or potassium, and the opposite face is going to be 0. So as I go across this pyramid, three-sided pyramid, I'll go from 0% of whatever is up here at the top to 100% of whatever is here at the top. So what we see is that the Yaozhou, the Ding, the northern glazes are way up here near 70% silica. And where they all are is, all the Y's are Yaozhou. Let's see, that's a Ding, and let's see, what's this one? That's northern whiteware of some kind. I don't know what it is. And so what we see is that the compositions, if we compare calcium, potassium, and the other one has got to be alumina up here at the top, alumina plus iron, and this is actually calcium plus sodium, and this one is, potassium plus sodium, and this one's calcium plus magnesium, and it's over here in this corner. So what we're going to see is that these glazes that are at about 60 to 65% are the Yue, Guan, and Lungchuan. So these are southern glazes. And then we can go up here and we can see the The Koryo and Puncheong glazes are very tightly fixed in a much smaller area, but they're down here at 60% silica. So the silica is far lower. They're on this bottom triangle right here. So we can differentiate the compositions. Not always, but most of the time. So all Korean glazes are in the upper diagram at or near about 60%. Let's see. And then this is really a reflection of these different geographic source areas. All right, that is the end of my talk, and the material that you've seen is published in 2 places. An article that Louise and I and Carol Handwerker wrote in a volume of an American Ceramic Society series called Ceramics and Civilization. And it also came from an appendix from an exhibit at the Chicago Art Institute that had many pieces from the Ataka collection, and my appendix is called The Technology of Korean Celadons. Lastly, I'd like to thank Louise Court and the Freer Gallery of Art Study Collection, Ra Soon-hwa, head archaeologist at Ewha Women's University, as well as the Kanjin Museum, the Pusan Museum, the National Museum of Korea, the Karita Museum, the Art Museum of the University of Michigan, and also the first shards, which are so difficult to get with a really good context unless you're on an excavation. I'd like to thank one of my MIT students who is a Peace Corps volunteer, asked what she could do in Korea in her spare time, and I suggested investigate Korean celadons. So she returned in 1986 with a few highly valued sherds from an excavation in Kanjin at a kiln that had been carried out by a high school archaeology class. Thank you very much.